Welcome. In this video lecture, I am going to talk about the time series exploration using R. So the time series exploration concept is very important when you want to predict the time series data. Okay, mean when you want to forecast. So that means you can say divide the time series data into different components such as the level component, the trend component, and the seasonality component. So these components are very important because they are indicating the pattern of the data. Okay, so because based on the pattern of the data, we are going to decide which type of the time series forecasting method we should apply. And in addition to this pattern, we have the random error. So we want to apply such a forecasting method that this random variation, or you can say the forecasting error, should be as minimum as possible. So right now I'm going to talk about how we can identify whether our data contain the trend component or not, how we should know that whether the seasonality component in our time series data is available or not. So for that, I'm going to use these two packages. Like one is the forecast package in R and another one is tsutils. Okay. So first of all, I'm going to talk about how can I translate the any data series, okay, into a time series form. Like as you can see that if I have the data set in years and we have the observation against every particular year. So in R, how can I translate into a time series? I should use the function called ts, then bracket start, that is a ts function, which is the c, which is concatenating these observations. Okay, so we are writing down the observation, and then I am stating that the starting year or the starting point is 2012. So once we run this, then we are going to store in a variable called y. So this time series data is going to be stored in a y. So if you want to store the monthly data, okay, so how you can do that? So we are saying that this is again a time series function. This is ts z, that is a variable in which we have the store the data, and then we are telling that the frequency is 12 because it's a monthly data. So that's why we are telling that the frequency is 12, and we know that in 1 year we have the 12 months, and the starting point is, we are mentioning that the starting point is 2003 is the year, and one is indicating the first month, which is a January, is the starting month. If the starting point is February, then you can write down 2 over here. Similarly, so that means in a time series, the most important thing is we have to mention these three things. One is the data, okay, the variable in which we have the data set. We have to mention the frequency, whether it's a yearly data or a monthly data or a weekly data or hourly data, and then we need to mention the starting point. So here I am giving the example of the daily data, okay, how you can mention it. So either you can mention the data in a frequency that is 7, okay, in order to identify the weekly or annual seasonality perspective, you can mention the number of days. So why we are using 365.27 in order to cater the leap years data, okay. So this is the number of weeks if we are considering these number of days. Okay, similarly, we can mention the hourly data, okay, or a daily seasonality perspective, okay, if we are considering, or a weekly perspective hourly, okay, data, okay, and then we have the annually perspective. So this is basically the in terms of if we have the data in the minutes. So let me see in the R. If I'm going to open it, so first of all, I need to install the forecast package. I have to need to install this particular package, which is tsutils. Okay, once we have installed it, then we can call these two libraries. Okay, and then I have the data set, three types of the data set. The first one is basically the ts1 text file. Okay, and then I am stating that the starting time period is 2011. So let me show you this data set, which is ts1. Okay, so as you can see that this is a starting point, and I am mentioning this is the The year starting point is 2011. So with the help of R code, okay, and then 1 is basically indicating the first quarter, okay, and this frequency is indicating that we are considering as a quarterly data, okay. If I'm writing down 12, then I'm considering as a monthly data, okay. So if this is TS1, if I am writing down over here is TS1, as you can see that we have the yearly data in terms of quarter wise, okay. Similarly, we have the TS2 data, okay. Then over here we have the monthly data, okay. So this is the monthly data we have. Similarly, we have the TS. So I'm just reading the data, okay. This is also the monthly data. This is also the monthly data. Now, what I am going to see is I'm storing this TS2 data, okay, into the Y, and then I'm plotting this particular Y. As you can see that, so we have on x-axis that is a time, on y-axis we have the data points. Okay, as we can see graphically that it took like there is a increasing trend. But in order to know the trend, we can perform different type of analysis. But before that, let me show you the that how you can call represent different type of the data in R. If you want to represent annually data, quarterly data, the frequency should be 4. Monthly data, the frequency should be 12. The daily data, the frequency should be weekly or hourly or half hourly even. Okay, and these are the starting point you have to mention while you are calling the function of TS. Okay, now let's do the trend analysis using R. So in order to perform the trend analysis, as we have seen in the R, that we should draw the time series plot. Okay, on x-axis we have time, on y-axis we have y, and with the help of this we are going to apply the centered moving average in order to identify whether there is any trend or not. Okay, so what this CMAV, that is a centered moving average data, Y is the variable in which we have the data set, and then output plot is equal to 1. Okay, what this function is going to do is it is automatically going to decide whether we have to calculate the centered moving average 3 quarter or a 4 quarter or a sorry, this is a monthly data, so whether it's a 3 month, 4 month, 5 month or a 15 month, it is this function is going to be decided automatically. But if you want to force it that it should apply 3 months moving average or a 4 month or a 5 month, you can do that. So let me show you. So, so here we have stored the data into the Y, we have plotted it. Now I am forcing it that it should calculate the 3 month moving average. So with the help of this, so I can calculate 3 month, that is CMA. Okay, as you can also see that on a graph, it is also showing us. Okay, because I have also plotted. Okay, so similarly, we can do the 15 months moving average. Okay, as you can see that as we are start increasing this particular value, so we can easily see the smoothness in the line, as well as it is also showing us some data point. Okay, so but if I am going without mentioning these number, let R decided that what should be the average they are should compute, then we can use this particular function without mentioning the moving average. So they have automatically picked the number, okay, and calculated the centered moving average. And with the help of this one, we can easily see that so there is a increasing trend or there is a linear trend, right? Now, might be possible that your data may have some missing numbers. If your data have this missing numbers, like in this particular data set which I have used, there is no missing number. But if there is any missing number, so the beauty of this particular function is if you are going to mention fill is equal to false, okay, so that is going to be calculated the missing number with the help of exponential smoothing method, okay, in order to fill that missing number. Okay, so remember that. Right now, as we can see with the help of this plot, that it look like that there is a linear trend, but we can also perform a test which is called as basically Cox Stewart test. Okay, how we can do that? With the help of this one, where h naught there is no change upward or downward, which means there is no trend, or h1 there is a change. Okay, so if I am going to run this particular command, that is this one, cox steward. Okay, it is saying that the p value is 0.313, okay, e power minus 10, so which is less than 5%. So what is going to be our decision? That if this particular p value is, if this particular p value is less than our pre-decided value, which is alpha 5%, so we will say reject h naught. So the reject h naught mean, so there is a change in upward or a downward, and as we can see from the graph, so there is an increasing trend, so which means the data must have a trend. Okay, so this is basically a non-parametric test. So you can also apply some other test in order to identify the trend analysis. Okay, the second component, if you want to find out the seasonality, so for that we have a function called SES plot y. Okay, so you can use these numbers in order to draw different type of plots. Okay, so let me show you how you can do that over the seasonality. First of all, I'm using the default seasonality plot, that is this one. If you are using 2, that is going to be this one. The remaining thing and the output would be the same, 3, 4. Okay, so you are getting different type of plots. So how you can interpret it? That is basically indicating this particular p value. So they are basically applying a non-parametric test, that is basically the Friedman test, and we can see that if the p value is less than or equal to 0, you can say less than 0. Okay, right now this is basically the p value. If this is less than, not only less than 0, which is 0.05. Okay, so if this p value is less than 0.05, then we will say there is a seasonality. But if it is greater than 1, then we will say there is no seasonality. As we can see that the p value is less than 5%, so that means this particular data set do contain some seasonality. Okay, so I hope you got the idea how we can perform the time series exploration using R in order to identify whether our data containing the trend or whether our data containing the seasonality or not. So thank you so much. See you in the next video. Welcome. In this video lecture, I am going to talk about some simple forecasting methods using R. Okay, as well as we will also discuss about how we can calculate the in sample forecast error, as well as how we can calculate the out sample forecast errors, and then we will going to compare those methods, which method is suitable for the particular data set. Okay, the first method we are going to discuss is the mean method, or you can say the average method. That is simply the future value is going to be the average of the historical data. That would be the mean method. The second method we are going to discuss is the naive approach, or you can say the naive method. So in this method, we are saying the future value is going to be equal to the last observed value, or the last actual value of the data set. Okay, so whereas in a seasonal naive method, we are saying that whatever the last season particular value is, those values are going to be equal to the future values. Like if I am saying that we are calculating the monthly basis forecasting values, and we are going to apply the seasonal live method, that mean in the last 12 months, okay, whatever those values are, that is going to be the future years, whole years, the forecasted value according to the seasonal knife method. And the third one, so over here basically y is basically indicating the yt is indicating the original values, h is the forecast horizon, that is the basically the seasonal period we are calculating m. Okay, whereas k is going to be calculated like this, that is basically a smaller integer number. Okay, whereas in a drift method, we are saying that the drift method, the forecasted value be equal to the last value plus change over time. Okay, so that is basically, this is the change we are calculating, or you can say drifting, which we are calculating, right? So let's apply these methods using R, and then we will also calculate the forecast errors as well. So for that, I am first of all needed the package of R that is called as the forecast package. Okay, so let me increase the size of this one, the code. Okay, so this is basically, first of all, I'm going to call the library that is the forecast, as well as I'm going to call the package called as the next package I am needed, that is tsutils. Okay, so these two libraries, first of all, we need to install and then call. So how we can call the libraries, that is with the help of these libraries. And then basically I am interested to forecast monthly time series data. Okay, so let me show you this data set, which is basically ts2. Okay, so these are the data set. Okay, that is basically the monthly data. Okay, as well as I have also created the out of sample. So these are basically the out of samples, or you can say testing data. This is basically the training data. Okay, so with the help of this training data, we can calculate the in-sample forecast error, and with the help of out-of-sample forecast error, or you can say with the help of testing data, we can calculate the out-of-sample forecast error. So first of all, I am going to read this text file. Okay, so how we can read it, that is with the help of scan function and then ts2.text. Okay, because this text file is in that folder where I have created this project. Okay, so that's why I am just writing down scan and then the name of the file. If that file is not available in that particular folder, that then you need to give the whole path of that particular file. Okay, then I'm saying that the start of 2011 one, which means I'm saying that this is the monthly data. So that's why I'm saying the data set of those values are starting from year 2001. So this one is mean that is the starting month is the January. Okay, and the frequency is 12, which is basically indicating the monthly data. If it was quarterly data, we can write down 4. Okay, if it is the annually data, we can write down frequency is equal to 1. Okay, so that means first of all, with the help of this ts, that we are converting this data set into the time series. Okay, and then I am storing into ts2. Then I am going to plot this data set. Okay, as you can see that on x-axis we have the time, on y-axis we have the actual data set, which is basically the you can say monthly data set. Now I am going to read the second text file, which is basically the, you can say, the test data, that is again a monthly data, and it is starting from 2016 for January. Okay, so now I am reading this one file, which is basically in ts 2.test variable. Okay, now I'm saying that this ts2 is going to be equal to y. That is basically we are storing this time series data set into a variable called y, whereas this test data set I'm going to store into y2, y dot test. Okay, then in order to find out the forecast horizon, I am calculating the length of, or you can say the number of observation in this particular variable. So how we can do that, that is length y dot test, so that is equal to h. So which means so the next 12 months are going to be our forecast horizon. Okay, so that is basically the number of values in the test data set. Okay, whereas if you want to see the original data set, which is y, okay, if I'm writing down, that is starting from 2011 January to December 2016, right? Whereas y dot test contains the test data values, right? Now I'm going to apply the first method, which is a mean method. How we can do that? That is with the help of mean function. So that is mean f, that is a mean forecast value. And then I'm mentioning the original values. So the original values are stored in a y. Then I'm mentioning the forecast horizon. I am saying that I want the forecasted value of the next 12 months because h is equal to 12. So if I run this one and then I am calling f dot mean, you can see that it is showing me the forecasted value from 2016, January 2016 to December 2016. So these are the forecasted values. These are the prediction interval at 80% confidence interval as well as the 95% prediction intervals. Okay. So if I want to see only the fitted value against January 2011 to December 2015, that is basically the in sample forecasted value. So I can use f dot mean dollar sign fitted value. So you can write down f dot mean dollar sign. So here we have the what kind of method we are applying, what are the levels. Okay, levels means that is the confidence levels. Okay, then over here you can find out the fitted value. So if I run this particular command, you will get the fitted value, or you can say the forecasted value against the uh, training data set. Okay. Okay, so these are going to be used when we are finding the forecast error within a sample. So now let me plot this forecasted value, which is f dot mean. If I am plotting this one, you can see this is basically the original data set. This is basically indicating the forecasted value, this dark blue line with the help of mean method, and this dark gray color is indicating 80% prediction interval. This light is 95% prediction interval. Okay, so let me call the future only the future. If you do not want to plot these, you can say the prediction intervals. You want to only access these forecasted values. So for that, you can write down the function f, write down the command f dot p dollar sign and then mean. Okay, let me show you dollar, and then over here we have a mean. If I run this one, you will see that from January 2016 to December 2016, because our forecast horizon was 12. Now, what I am going to do is I'm converting into the time series of these mean values, these one, this one, as well as I am saying the starting point is equal to the f dot test, which means the starting point of this data set is January 2016 and the frequency is going to equal to f dot test, and how much frequency, that is 12 months. So first of all, I am converting into this into the time series. Then I am going to plot, which is with the help of TS time series plot. This is the original values that is going to be shown to me. These are the test values. Okay, this is the forecasted value. So the original values is going to be shown with the blue color. Test value is also going to be shown the blue color, whereas the fitted value, or you can say the forecasted value, basically are going to be shown in the red color. So if I am going to run this command, so you can see that these are the actual data set. These are basically the forecasted values. So this one is basically the you can say with the help of mean values. Okay, not sorry, this is not the forecasted value. Basically, this is the test values. This is basically the forecasted graph. Okay, now the same procedure we can use to find out the Naïve forecasting method. So there are a number of ways to find out the Naïve forecast method in R. The first approach which I am going to use is I am going to use the function of replication of the tail, the original values of the last original value, okay, up to forecast horizon 12. So if I run this particular command, okay, and you can see that it is showing me the last value. So if I am saying this one, this is 3088. So this last number is going to be repeated 12 times. Okay, as you can see, because our forecast horizon was 12. So there is another way that we can use. So we have the Naïve function. Okay, and I am saying original value. This is I am showing that the forecast horizon is equal to h, which is 12. So let me run this command. We are going to get again the original forecasted value as well as the 80% confidence with the help of this particular function. So in order to get the fitted value, so I can run this again particular command in order to get the within a sample forecasted values. Okay. So you can also get the Naïve forecast value with the help of the function RWF. Okay, that is also giving us the same forecasted values as we are getting previously. Okay, that is this one. Okay, so similarly, I'm doing the same thing which I have done with the mean method. I'm going to convert the forecasted value into the time series. So this is basically the mean values with the help of the Naïve. These are basically the forecasted values. Okay, so this is basically the future forecasted value, right? So the start time is, I am saying that the y dot test and the frequency is equal to y dot test number of values. Okay, if I run this, and again if I am going to plot this one, so this is the original data set, this is the test data set, and this is the forecasted value with the help of Naïve approach. So now we are going to apply on a seasonal live method. Again, in order to find out the seasonal live method, we can use either the manual way, which is basically using the built-in R function, that is repeat the tail values of y, okay, and then we are mentioning comma how many time it is going to be repeat, that the frequency of the y. So that is the number of values of the y, okay, and then how many time it is going to be, that is basically we are indicating the seasonal component, okay, divided by the forecast horizon. Okay, so this is going to be equal to the 12 future forecasted values, right? Now, if you want to use the proper seasonal Naïve method, you can use this particular function S-Naïve. This is the original value. This is the forecast horizon. So we can do this way as well. So again, in order to find out the within a sample forecasted value, we can use $fitted. Again, I am converting the future forecasted values as well as the time and the frequency in order to convert into the time series, and then I am plotting it. So again, this is the original data set, this is a test data set, this is a Naïve forecast method. Okay, so as we have seen from different three graphs, so this is the mean method, this was the Naïve method forecasted value, this is the seasonal Naïve method. It looked like among these seasonal Naïve method is the better one. So let me find the forecasted value with the drift method as well. So in a drift method, we can use the function RWF, that is random walk forecasted value. So we are saying that a y, okay, and drift is equal to true. Okay, we have to mention this one. Okay, then we can run this one in order to find out the in sample $fitted future, converting the future values in the time series, and then we are plotting. This is the drift method. Now, in order to check the accuracy, mean which method is better within a sample or in a out of sample. So, in order to find out the forecast accuracy of the within a sample, so how we can do that? We can use the function accuracy from the forecast package. F dot mean, that is the fitted value, which is the training data sets of fitted value, or you can say the corresponding to the training data set. This is the actual training data set, and this is I am using in a mean variable. I am calculating this one. Okay, so let me do this one. Why it is I'm getting error? This is the mean fitted value. Okay, this one. Let me run this one. Okay, and then I am going to again run this particular command. Okay, now we are getting this one fitted value. Okay, now I have to do this one again. This is y fitted values. This is again S knife fitted value. Okay, again we have to, let me run this one again. F knife, this one. Now we are getting fitted values. This one. So again, I'm running this one. Okay, this one. Now we are going to calculate the accuracies of all three methods with the help of mean, Naïve, seasonal Naïve, as well as drift. And then with the help of this R bind, that is a row bind function, I am saying that I am going to combine row wise these three variables, okay, and I'm storing into f dot all. and then I'm giving the name of those rows. Okay, so basically to the mean, I'm saying that the give the name of the mean, then Naïve, then seasonal Naïve, and drift. Okay, so basically giving the row names, and then I'm calling it. As you can see that with the help of those accuracies, against the mean method, if I'm using root mean square method, the best method is basically the seasonal life method. If I want to use the mean absolute error method, then the best method is the drift method. If I am going to take the decision with respect to mean absolute percentage error, then the best method again is a seasonal knife method. That was a within a sample forecast error. That is normally is not a good approach. So the better decision is that we should take out of sample, which means we are going to calculate using the test data. Okay, so for that, we are using the forecasted value and the actual test data. Okay, that is again going to, I'm using the same command. Now, with the help of these out of sample, we can say that if I'm using root mean square error, the best method is a seasonal knife. If I'm using mean absolute percentage method, the best one is the drift method. Okay, similarly, if I'm using simple mean percentage error, again drift method. So against mean absolute error, the best method is the drift method. So depending upon what kind of measure of accuracy you are using, you can pick. So we can see that with the help of mean absolute percentage error, with the help of mean absolute error, as well as with the help of mean percentage error, the drift method is giving us the better forecast compared to other. I hope you got the idea how what are the simple forecasting methods are which we can use to predict the especially the fast moving data, such kind of the data. Okay, and how we can find out the within a sample forecast error as well as the out of sample forecast error in order to select the best forecasting method. So thank you so much. See you in the next video. Welcome. In this video lecture, I'm going to talk about how we can apply the exponential smoothing methods in order to predict the time series data. Okay, so as we know that whenever we are going to talk about the time series data, especially when we have the fast moving demand, so we discussed this type of demand in our first two lectures. Okay, the first one we talked about the time series exploration, in which we talked about that we can divide the pattern of the time series data into three component. One is the level component, another is a trend component, another is a seasonal component, right? And then based on the particular components, we are going to decide what kind of exponential smoothing models we should apply, right? So if we have only the level component and there is no seasonality, so we can apply N and N model. So N and N model mean we can apply simple exponential smoothing method. Okay, but if we have the level component as well as we have the additive seasonality, we can apply this particular model, okay, which is NA. That means there is no trend component, but there is a additive seasonality. So there is no trend component, there is a multiplicative seasonality, right? As we can see over here as well from a graphical perspective as well. But if we have an additive trend and there is no seasonality, then we can apply A and N model, which is also known as Holt's linear trend method, right? But if we have the additive seasonality, if we have the multiplicative seasonality, as you can also see from the graphical perspective, if we have the damped trend, this is the damped trend, right? Downside perspective, this is the exponential trend. So all these models can be applied using R. So A and A, that is known as additive Holt-Winters model. Okay, that is this one, right? Similarly, if we have the multiplicative, that is known as Holt-Winters method, that is we have the multiplicative seasonality. Okay, if we have the damped, then we can say is the damped multiplicative Holt-Winters method. Now let's see the formulas of these models or these methods. This is basically the simple exponential smoothing formula where LT is indicating the level component in time t, Alpha is a weightage value which is always lie between 0 and 1. So we have to pick the value of the alpha, whatever the alpha value is going to, we are going to pick. And of course, as we are going to develop these models using R, so R is going to pick the best, or you can say the optimum alpha. So by itself. And then YT is indicating the original time series data. So LT minus 1 is basically indicating the previous forecasted value, or you can say at time t minus 1's level component. And again, as we have discussed, the total alpha should be equal to 1 because this is a weightage value. So if this is alpha, this is going to be 1 minus alpha, right? So the future forecasted value would be equal to LT, no matter what is your forecast horizon. Either you have the forecast horizon of one time period or a two time period or three time period, this value is going to be repeated, okay, for the every future value. Similarly, so this is basically the simple exponential smoothing formula, okay. If I'm going to talk about the Holt's linear method, here we have the level component, we have a trend component, okay. And then in order to find out the forecasted value, the forecasted value would be equal to level plus trend, and the trend component is going to be multiplied with the forecast horizon, okay, whether it is 2 months or a 3 months or a 4 months, that is going to be multiplied with that one. So let's understand, this is basically the alpha value, that is a weightage value, this is the original time series, this is last time period level component, this is last time period trend component. And in order to calculate the trend component, we have to find out the value of beta, which is again lying between 0 to 1, okay. That is R is going to pick automatically. This is the current time period level component, last time period level component, this is the last time period trend component. Similarly, if I am going to talk about the additive Holt-Winters method, where we have the seasonality component as well. So in order to find out the level component, we have alpha, original time series. This is a seasonal value, okay. That is basically T is indicating the current time period. M is basically indicating the number of time period in a particular season. If we have whether we have a 3 month seasonal time period or a 4 month seasonal component we have. Okay, so depending upon the number of periods in a season, that would be going to be the value of M. Okay, so this is last time period level component. This is a trend component. So in order to find out the trend component, that is the same. So this is the seasonal component. So gamma again is a weighted value which is lying between 0 and 1. YT is the original time series data, which we have the historical data. This is last time period level component, trend component, and this is a seasonal component. And if we have saying that this is additive approach, then the forecasted value would be the level component of this time period. And this is basically indicating the you can say trend component multiplied by the forecast horizon, okay, plus we have the seasonal component. Similarly, we have, if we have the multiplicative, if we have additive, uh, you can say damped trend, then these are the formula. If we have the multiple damped trend, if we have the simple multiplicative, we can use these particular formulas. Okay, now let's understand this particular formula. So I'm going to explain this particular formula, how it is look like. Basically, we want to understand how exponential smoothing method is going to assign the weight, that means the value of the alpha. If we see that the LT is basically equal to alpha YT plus 1 minus alpha LT minus 1. So if I am going to replace this LT minus 1, means further if I am opening this formula, so we can see that LT minus 1 is going to be equal to this one, which is alpha YT minus 1 plus 1 minus alpha LT minus 2, okay. So that is basically the original data. This is last time period level component. This is t minus 1's original data, then the previous time period, which is t minus 2 level component. Okay, so if we simplify, we got this one. Now if I further open this one, and then if I'm going to further open LT minus 3, and then if I'm further opening LT minus 4, I'm going to get this time series, which is basically, this is the initial value, okay. This is the current, you can say, value. So now we can see that as the time period goes backside or the backward side, the value of the alpha is going to be start decreasing exponentially. Okay, so in an initial, let's say if we are going to the value of alpha zero point 0.2, so this particular value is going to be less than zero point 0.2, and this value is going to be less than from this one. Okay, so that's why we are saying the weightage of the previous time period is going to be lesser and lesser. Okay, that's why we are saying that this is the exponentially we are assigning the weightage to the previous values. Okay, so the more current value it is, higher the weightage is going to be assigned by the exponential smoothing method. Now let's talk about how we can implement these methods in R. So we have the different approaches, or you can say we have multiple functions available in R, which we can use to implement it. Like we have SCS, which can only be used to apply for the simple exponential smoothing method. We have the Holt function, which can be used to apply A and N. When we have the additive trend, there is no seasonality. We have damped trend, there is no seasonality. Multiplicative trend with and no seasonality. Okay, so these are the methods can be used to by using the function of Holt. And then in order to apply these method, we can use this particular function. Similarly, we can use Holt-Winters function. So let's see how we can apply these exponential smoothing methods using R. So for that, first of all, I need to load the required libraries. I'm using the package forecast. Okay, so I'm also loading this library package, as well as the third one, which is tsutils. Okay, so basically I'm going to use the time series, this particular data, which is basically a monthly data set. Okay, so as you can see that I am reading this time series with the help of the function ts. Basically this function is going to convert the data series into the time series. So reading the data with the help of scan, so I have already stored having the data in a text format. Then I am mentioning the starting time period. Okay, so I'm saying that the first data set we have for the January 2011, and the frequency is 12, which means this is the monthly data set. Okay, now if I'm going to plot this time series data, as you can see, this is year and these are the values. Now what I am going to do is I'm basically, if we are going to check this ts2 data. Okay, so we can see from 2011 January to December 2015 we have this one. So I have already break this time series data into two component. One, this is basically, you can say, the training data set we have. Now I am going to use the testing data set in order to check which model is going to be the best one. So that is basically I have stored in ts2.test. Okay, that is another data file we have. If I am going to uh, um, call this one, so you can see these are the 12 data points we have. Okay, so now in order, I'm assigning this ts2 in another variable, which is y, as well as ts2.test another y, and then I am assigning the forecast horizon, which is the length of the y dot test equal, which is the 12 months. Now let's see how we can apply the simple exponential smoothing method. That is basically YES. Okay, sorry, SES, that is simple exponential smoothing method. Then I am saying Y is indicating the variable in which we have the data set. Okay, H is equal to H, mean that is we are assigning the forecast horizon, or either you can write down over 12 over here. So if I run this one and then F dot SES, so we can see that this is basically the simple exponential smoothing forecasted value. Okay, so starting from January 2016 to December 2016, so these are the forecasted values. These are at 80% prediction interval as well as 95% prediction intervals. Okay, let me see f dot scs, that is the variable in which we have the results. So if I'm writing down dollar and then model, okay, you can see that if I am running it, it is showing that we have applied this simple exponential smoothing formula, and what's the value of alpha R has selected, and what was the initial value. Okay, if you remember, we have the formula in which we need the LT minus 1 value. Okay, so this is the initial value that is assigned by the R. Okay, and then it is going to be calculated these information criteria that is basically called as Akai information criteria. This is the corrected Akai information criteria. This is the Bayesian information criteria. Okay, normally these criteria are used in order to select the best model, and usually these methods are always used in a comparison way. So lesser the AIC or AICC or BIC values are, the better the model is. Okay. Now, if I am saying f dot ses dollar sign, okay, if I'm clicking the mean, okay, so what are going to be showing us? That is only showing us these forecasted values. Okay, then it is not going to show us these confidence intervals. So these are only the forecasted value with the help of this particular command. So you can further explore this one. Okay, dollar sign, if I am saying show me the fitted value, that is basically against January 2011 to 2015. Okay, December 2015. So we have the actual data set, and these are the fitted value with the help of simple exponential smoothing method. Okay, now let's plot this one. Now I'm what I'm going to do with this function, that is I'm saying convert the time series data, and then I'm using the mean values, that is the forecasted values, and then I am saying the start date is going to be equal to whatever the start date in y dot test, as well as the frequency should be equal to whatever the frequency of the y dot test. Okay, then I am plotting the original data, then the test data, then the forecasted value. Okay, and then I am mentioning that the original data line should be blue color, the test data set should be blue color, and the forecasted value should be in a red color. So if I'm running this one, so you can see that this is the original data set, this is the you can say test data set, and these are the forecasted values. So this is how we can get the prediction plot with the help of simple exponential smoothing method. Now let me apply the Holt's linear trend method. So for that we can use a function Holt. Okay, then y is this the variable in which we have the original data set, then we are setting the forecast horizon, we are saying damped is equal to false. Okay, so that means there is no damped trend right now. Currently consider this linear trend. So if I'm running this one, again we are getting these are the forecasted values. Okay, these are the confidence intervals. So if I'm again using f dot Holt linear dollar sign, so if I'm saying model, so it will show me the name of the model, which is a Holt method, which is a Holt's linear trend method. It is showing us the optimum value of alpha as well as beta, and the initial value of the level component, the initial value of the trend component, as well as the information criteria. Okay, let me say I want to apply Holt's exponential trend method. So then I can use damped is equal to false, and then exponential is equal to true. Okay, so now if I am running this one, okay, so we can see that this is Holt's method with exponential trend. Now if I am saying that whether the linear trend is better or the exponential trend is better, so based on Akai information criteria, this is 937, and this is basically 941. It seems that the Holt's linear trend method is not better, but the exponential method is better because it has the lesser information criteria as well as Bayesian information criteria as well as the corrected one. So this one is the better one. So let's try that. We have exponential is equal to false. Okay, so this is basically false, but the damn trend is equal to true. Okay, now we are saying that apply the Holt's damped trend method. Okay, so this is with the help of damped Holt method. If we see that the information criteria is 942, but this one is 937, so that means the exponential one is the better one. So this should be the false. So this should be okay true. Okay, and now if I'm running this one, so with the help of Holt's exponential trend method, we are getting this prediction values. Okay, so I hope you got the idea how we can apply the Holt's simple exponential smoothing method in R, as well as Holt's linear trend method in R, as well as damped trend perspective. Similarly, if you are interested to exponential smoothing. Okay, so right now by default it is applying the additive. Let's say if I want to apply the Holt's uh, exponential trend method with multiplicative approach, then you can write down type is equal to okay, then you have to write down multiplicative. Okay, and then you can run this one, right? Now it is basically showing us the Holt's uh, exponential trend method with multiplicative approach, right? So if you write down over here additive, it is going to be apply the additive approach. I hope you got the idea how we can apply the simple exponential smoothing method in R, as well as Holt's linear trend, Holt's exponential, damped, additive, multiplicative. So thank you so much. See you in the next video. Welcome. In this video lecture, I am going to talk about the forecasting methods to predict the intermittent demand. So let's first of all discuss what is the difference between the non-intermittent and the intermittent demand. Okay, so here you can see that in a blue line in this particular graph that is showing the non-intermittent demand, which means there is no zeros in the actual demand values over the time period. Wherever so this on the bottom of the graph, if you can see with the orange line, it is indicating that so there are few time periods when we have the zero values in a particular demand. Okay, so we have a certain demand value, but there are a time period when we have the zero values or a zero actual demand in a particular time period. So whenever you have the demand values exactly equal to zero in some time periods, and in some time periods we have the certain demand values, that is called as the intermittent demand. Wherever if we do not have any zeros in the actual demand, that is called as a non-intermittent demand method, demand values. Okay, so of course, if we are going to talk about the forecasting method perspective, if you are going to apply the normal methods such as exponential smoothing methods, or you can say autoregressive integrated moving average methods. Okay, so whatever the method, if we are going for the non-intermittent demand methods on the intermittent demand, we are not getting the appropriate forecast values. So which mean we have to use certain methods which can predict this intermittent demand. So as we said that when the product experience in a several periods zero demands, okay, so then it is called as the intermittent demand. Okay, often the demand is small, okay, and the variable size. So certainly maybe we have the demand period 2 months, we do not have any particular demand of a particular product, and then suddenly we have a demand, and then again next 2 to 3 months we do not have the demand. Okay, maybe the time period could be the month, could be the week, could be the days. Okay, so this sort of you can say the trend of the time series data we can observe in the aviation industry, in automotive, defense, manufacturing, as well as the retail industry, where we can see that such kind of product demand of over the time period, which is the intermittent demand. And moreoverly, the product having the end of their life cycle, you can observe the demand of the intermittent demand. Okay, so for that, we cannot apply, as I told you earlier, the usual forecasting methods. So for that, we have to observe, is there any appropriate forecasting method which we can use to predict the intermittent demand. So here we have few methods. We can categorize into the three categories. One is ad hoc methods, we have model-based methods, we have alternative methods. So here I am going to talk about the Croston's method as well as some adjusted methods, which are, you can say, the improved methods of the Croston's. Okay, and then I'm going to talk about some temporal aggregations, so using R. Okay, so let's first understand how the Croston methods works. Okay, so first of all, in a Croston method which he proposed in 1972, he says that we should separate the intermittent demand into the two components. And what are the two components? One is non-zero demand time series, another is inter-demand interval time series. Okay, so what does that mean? Okay, so let me open the R, and for this we need a library called ts intermittent. Okay, that is a time series intermittent. Okay, so I have already installed it. I am running this library, or you can say running this package, and then I am basically reading a file that is called as ts3.txt, in which we have a data set, and I am saying that the starting point of this time series is January 2011 with the help of this command. And then because it is a monthly demand, okay, that's why we are setting frequency is equal to 12. So if I run this one, okay, and then I am clicking writing down the y, because all the this time series we have stored in the variable called y. So as you can observe that, so in January, February we have the demand, but in March we do not have the demand. April, May. Okay, so first of all, what we need to do is we will see the composite of the two things, right? Non-zero demand series as well as inter demand interval. Okay, how we can do that? We can do that with the help of this particular function, which is cruston dot decompose y. So if I run this one, now you can see that they have, with the help of this function, we have decomposed this particular series into the two intervals, which is non-zero demand time series as well as inter-demand time interval. So how you can read it, as you can see that the first value is 132, then 22, and then there is a zero. So we are not writing down this one, only writing down the next period in which we have a demand, then next period 159. So over here in interval we have to write down against every demand size what was the time interval. In a particular month, whenever we have a demand, we are going to write down 1. Okay, 22 again 1, and then after 22, so after how many number of months we have the demand, so that is 1 and 2. So this is after second month we have the demand, so that's why we have written down 2, then again 1 2. Okay, that's why we have the second 2, then 1 2. Okay, again we have the third 2, then 1 2. Okay, so that is this one, then we have 1 2, and then in the third month we have the demand, that's why we are writing down 3, right? I hope you got the idea how we can decompose this time series into the demand size as well as the interval size. So over here you can see that we have this against these values. So after this one we have 0 1 3, so this 3 is indicating against 31. So against 74 we have 1, we have against 190 we have 1. So this is 0, so that's why there is no interval, because there is no non-zero demand, right? Okay, so I hope you got the idea how we can decompose, okay, or separate the non-zero demand time series as well as the interval demand inter-demand interval time series. Then what we are going to do is we are going to use both the series, or both the part of this time series. One is called as the demand size, another is called as inter-arrival time. We use the simple exponential smoothing method to predict these two series separately. Okay, and then once we predicted it, okay, what is the average demand size of the future, what is the average inter-arrival time, then we can calculate the average demand per period. So how we can do that? Simply, if we are saying that the average demand is 8 and inter-arrival time is 2.1, we can divide this number and we can get the forecasted value. So these are the, if there is no zero value, or you can say we have the non-zero demand, then we can use again simply simple exponential smoothing method using this is basically the demand size. This is for the interarrival time series. So you can see that we have the formula of the simple exponential smoothing. Alpha is the smoothing factor, xt is basically the actual demand, zt is basically estimated the non-zero demand size, whereas q is indicating the number of consecutive non-zero demand periods. So vt is basically indicating the interval size, right? And this is how we can calculate the forecasted value. Yt plus 1 is indicating the future forecasted value. But if we have actual demand is equal to 0, then zt plus 1 would be equal to the previous value of your non-zero demand size. This is basically interval time period, okay, or you can say interval size. This is a forecasted value. So remember that if your demand occurs in every time period, then Croston estimator, or you can say the Croston method is exactly equal to the simple exponential smoothing formula. So let me first calculate the forecasted value using R with the help of Croston method. So for that, again, I am running this particular command. With the help of this command, we are reading the file, that is ts3.text. We are saying the starting value, we are saying the frequency. So this is basically the training data. And then we have test data in a file called ts3out.text, so which I am storing into the y.test variable, okay, which are the 12. And then I am setting the forecast horizon, that is equal to the length of the test data, which is equal to basically the 12, because we have the 12 items, okay. And then we are plotting the actual data, which is y, okay. As you can see, this is the intermittent demand, which we have seen over here as well, okay. And then as we have decomposed it, now I want to predict. So using how we can apply, we can apply the Croston method from the package ts intermittent. The function name is crossed, crost. Then the variable in which we have the actual data set, we are setting the forecast horizon. And then we are also saying that plot this forecasted value. So if I run this command, so after this we have stored into the variable called f dot crossed. So they have plotted the fitted value as well as the forecasted value, as well as you can see that they have also given us the forecasted value with the help of Croston. This is forecasted value within, this is out. Okay, these are the values of alphas, as you can see in the formula. Okay, so the alpha values, these are basically the weightage values. Okay, and then we have the demand size, interval size, demand size, interval size. Okay, so this is within a sample, this is out of sample. Okay, so let me select these values one by one. First of all, I am taking the values of alphas. Okay, this is for the demand size, this is for the interval size. What kind of model we have applied, that is the Croston method. And then with the help of this one, we can see the component values, okay, the demand size values, as well as the uh, interval time. This is with the help of this one, we can get the within a sample forecasted value, or you can say the fitted value. This is giving us the out of sample forecasted value. Now the question is how we can interpret this numbers. Okay, the interpretation can be done. Let's say we have predicted the demand size. The demand size is 3.91 and interarrival time is 1.41. Okay, so if I'm going to divide this 3.97 divided by 1.41, as we have seen our formula, that is this one. Okay, so this is basically the demand size. This is interval time, that is 3.97 divided by 1.41. So we are getting 2.81, because the forecast horizon was 5 days. So next 5 days we have the demand of the product is equal to 2.81, 2.81, and so on. So if we are saying that, so for next 5 days, how many products demand we are going to receive, that is going to be 2.81. That is the average demand of any particular day multiplied by 5. So the total demand would be the 14 for the next 5 days. I hope you got the idea how we can get the forecasted value with the help of Croston method of the intermittent demand and how we can interpret it. Okay. So if I'm going to talk about the variation of the Croston method, because different authors says, like these authors says there is a biasness in the Croston method. So how we can especially what kind of biasness is, they are saying that if the demand size and the inter time interval of the demand is independent, then there may be the biasness. So different authors gave us the different you can say adjustment approach to make this estimated biased unbiased. Okay, like the SBA gave us this particular thing. They are saying that the future forecasted value, if I going to multiply with 1 minus alpha by 2. Similarly, these authors also gave us some you can say the estimator or the additional adjustment factor. So these authors saying that instead of giving taking the inter time interval of the demand, we should be taking the probability, okay, of the demand. That means estimating of the demand. That is indicating instead of taking the time interval, we are going to take the probability of PT, which means whenever there is a demand, the probability is 1. When there is no demand, then there is a 0 probability. So using that this approach, they have basically predicted the intermittent demand. So what I am going to do is I am going to apply all these methods in R. So how we can do that? So first of all, we have apply the Croston. Now I'm going to apply the SBA method. So how you can apply this SBA method, which is this one, okay? So you can apply this one simply using the same function crossed, the variable in which we have the actual data set, forecast horizon, and in a type we should write down in a double quote SBA. Okay, so if we run this one, okay, we got the forecasted value with the help of this method. This is I am getting the out of sample forecasted values. Okay, and then that is against the 12 months. Okay, in every month how many the what would be the forecasted value. Then I'm going to apply the third method, which is this one, which is in 2006 they have proposed this method. So let me find with the help of the same function, only we have to type is equal to SBJ. And in order to apply TSB, then we have to use the function called TSB, name of the variable in which we have the actual data set, and H is equal to H, which is a forecast horizon. Okay, now if we run this one, so these are the forecasted value with the help of this TSB. I hope you got the idea regarding these methods, which are mostly or you can say widely used to predict the intermittent demand, which is basically ad hoc method. Let me discuss some alternative method, which is a temporal aggregation method. So the first one I'm going to talk about that was proposed by in 2011. So that is called as aggregation disaggregate intermittent demand approach. Let's say the actual demand is this one, which is a monthly demand. So in month 1 we do not have any demand, in month 2 we have certain demand value, in month 3 we do not have any demand, in month 4 we have certain values, and so on. So what we need to do is, this monthly demand is intermittent. We need to aggregate in such a way that every month we should have certain demand. So, but the question is, that is the major problem. At what level we should aggregate? Should we aggregate quarterly, bi-monthly, 3 monthly, or you can say 6 monthly, and so on. So let's say if we aggregate this one quarterly, okay, so which means the sum of the demand of these 3 months, the sum of demand of these 3 months, then sum of demand of these 3 months. So this is basically at the aggregate level. Once we aggregated it, and then what we are going to do is we can apply any fast moving forecasting method. Fast moving forecasting method means you can apply Naïve approach, you can apply the simple moving average methods, or a weighted moving, exponential smoothing, RIMA or ARMA models. Okay, you can apply any particular model of the fast moving demand, in order to predict the future value. So let's say we have applied the Naïve approach. That's where the next quarter, the eighth quarter forecasted value is exactly equal to the seventh quarter. And once we got that forecast value, now we have to disaggregate. Okay, so disaggregate means, and because we have aggregated quarterly, so that means we are going to divide this value on a 3. So we will get the every month, you can say the next quarter forecasted value of every month of the next quarter, that is the with the equal weightage. Okay. So, and similarly in 2014, so these author proposed another method which is called as multiple aggregation prediction algorithm. So what does that mean is, so basically what they are doing is we have the total aggregation level. Okay, so they are basically aggregating at different months, or you can say k, they are setting into the different months, and then using those aggregations they apply the exponential smoothing method or any method you can apply, and then they are basically forecasting the level component, trend component, seasonal component. Okay, at the end every level they are basically calculating level, trend and seasonal component, and then only the level components, the average of level component, similarly we have the average of trend component, similarly we have the average of seasonal component. If we sum these components, we are getting the future forecasted value with the help of this multi aggregation prediction algorithm. So let me apply these methods in R. First of all, I'm going to apply the multiple aggregation method that we can apply with the help of function IMAPA from the same package of intermittent. Okay, so if I run this one, so we are getting the forecasted value. Similarly, I'm going to apply the intermittent aggregation level. This is basically IMPA. Okay, so we are saying make it as a vector. Okay, then y forecast horizon, and then the minimal and the maximum, which is basically h plus 1 and this one. Okay, so this is basically we are applying these methods. Okay, so once we have get the predicted value, so over here I am basically calculating the forecast accuracies for all the methods for Croston, SBA, SBA, okay, and so on. So how we can do that? We can use cbind function, and then the you can say the predicted value. Okay, uh, and I'm storing all these forecasted value in a variable called f dot all. Then I'm giving the column name, which means this is basically the Croston methods forecast value. This is basically SBA. This is SBJ, and so on. Okay, so after giving the column name, now I want to find out the forecast accuracies. Then I am finding, or you can say storing the dimension of this variable into a variable called k. Okay, so if you can run this command k, okay, you can see that they have the 5 dimension, which means we have the 5 methods. And then I am basically taking the cross product of replicating the test values. Okay, so these are the test values, and then I am, with the help of this one, I am repeating one up to k time, which means 5 times, and then I'm basically cross taking multiplying the cross product with this one and the test values, and taking the transpose. If I run this one, and then I'm saying f dot all. Okay, so as you can see that these are basically the resulting values against. So now we can easily calculate the you can say the errors of all. So this is basically y dot all, which means this particular matrix minus f dot all, that having all the methods forecasted values. Okay, so if you run this one, f dot all, okay, you can see that against the cruston we have the forecasted value. These are the original values. So against SBA, this is the forecasted value, this is the original values. Now basically I am calculating the errors. Then with the help of this one, I'm calculating the mean average errors. Okay, root mean square, Okay, and then I am combining these two and then printing. So this is basically average error. This is root mean square error against all the methods. So for this particular time series, which one is the best method? With the help of, if we are going to talk about the root mean square error, the smallest one is that is 93 point. That is basically the Croston one is the best one, method based on the root mean square error. Okay, if we are going to talk about with respect to ME, that is also the Croston method is the better one compared to the others. Okay, I hope you got the idea. So thank you so much. See you in the next video. Welcome. In this video lecture, I am going to talk about the forecast evaluation approaches. So normally, whenever we are going to apply any particular forecast method on a data set, so there are three approaches which we can use to evaluate the particular forecast method. One is called as in-sample forecasting evaluation approach. Okay, in-sample. The second one is known as out-of-sample forecast approach. Okay, and then the third one is called as rolling horizon, or normally it is called as rolling origin forecasting method, which is also known as time series cross validation for approach to evaluate any particular forecast method. So let me first of all discuss, in order to evaluate the forecast, what kind of information we have to find out. So the information we needed to evaluate the forecast is, that is the residuals, or we can say error of the forecast. So how we can calculate the residual or the error? That is basically the actual value, or you can say the observed value, minus the predicted value or the forecasted value. That would be called as the error or the residual. And the assumption is, so these errors must be uncorrelated. Okay, as well as the average or the mean value of these error must be zero. If they are not, then the forecast is basically the biased, right? Similarly, if the errors are not uncorrelated, which mean if they are correlated, then some information is left in the residuals. Okay, so that should be used in computing the forecast. So which means these are the two main assumptions that we are considering while we are finding the forecast error. Whereas the useful properties with respect to the prediction error is, when we are predicting or when we are forecasting the values, so we are saying that the error variance would be remains constant, as well as the error follow the normal distribution. As we are showing over here is one step forecast ahead. Okay, one step forecast residual means one step ahead, one time period ahead forecast error. Okay, no, in order to calculate the accuracy of the particular forecast method, we have multiple type of measures, whether we are finding the forecast accuracy with respect to in sample or out of sample or a rolling horizon. So we have mean absolute percentage error, or we can simply calculate mean error. Okay, we have mean square error, root mean square error, mean absolute percentage error, mean absolute scaled error. So these are the different type of measures which we can use to check. Of course, all these measures, smaller the measure is, or you can say smaller the value is, the better the forecasting approach is. Okay, so some of them are the scale dependent, some of them are the scale independent. Like, so these are the scale dependent measures, whereas these two are the scale independent measures. Okay, which means they are not depending upon the unit of a variable or unit of the error. So they are independent from the unit, right? So remember that, so individually these measures are not telling us anything. Smaller these numbers are indicating better the forecasting method is. So we always use these measures in a comparison perspective. So once, let's say, we have applied the exponential smoothing method, okay, or we have applied the ARIMA method, okay. Once we have predicted with respect to exponential smoothing, once we have predicted with respect to ARIMA, and then we are saying that based on mean absolute error, which forecasting method is better. Obviously, the method which is giving us the smaller mean absolute percentage error is going to be better. So which means the choice of these measures of forecast accuracy is also very important, whether you are going to select the forecasting method based on root mean square error, mean square error, mean absolute percentage error, mean absolute scaled error, and so on. So remember that some of these methods are good in some scenarios, and same as some are doing in other scenarios. So you have to pick appropriate measure of accuracy, okay, whether you want to use scale dependent or a scale independent measures of accuracies. Okay, in addition to these methods, we have furthermore in 2013, so these two authors basically gave us another measure which is called as relative mean absolute percentage error, where this is the MAE, mean absolute percentage error of a your model which you are considered, and this is basically the benchmark model's mean absolute percentage error, which is giving us the best forecast. Or either 2015 they gave us mean absolute percentage error, and this is the average in sample errors data, right? So that is basically how you can calculate the scale absolute percentage error. So you can check this particular link in order to see more measures of accuracies approaches, right? But like the main concern of this video is that we are going to find out the measures of forecast accuracy. Okay, whether you want to find out the accuracy, forecast accuracy in sample, out of sample, or a rolling horizon basis. Okay, as you know that when we are saying in sample, what does that mean is, so normally if I am saying we have the 100 value data set, okay, like as I'm showing over here. Okay, let's say we are saying the blue color is basically indicating the training data. Okay, this is training data set, and whereas the red is basically indicating the test data set. Okay, so if I am using this training data set to fit the model, and then again in order to find out the residual of the forecast, or you can say forecast errors, okay, and then again calculating those measures of accuracy such as root mean square error, mean absolute percentage error with this within sample data, as well as the forecasted value against those data, which mean I am considering in sample forecast errors to select the best model, which is not a good approach because it might lead us to overfitting the model or underfitting the model. Okay, so the better idea is that we should always try to report at least out of sample forecast error or a rolling horizon. So what's the out of sample? Out of sample means we are going to use the training data, okay, that is this one, for fitting the model, or you can say estimating the model parameters, whereas we are going to test the out of sample. Okay, so like as I'm showing you over here, so we have fitted the model using the blue dots or the blue data set, whereas these data set we have hold out in order to test whether this particular forecasting method is doing good or not. Okay, so using this data set, we are going to calculate the different type of measure of accuracy, root mean square error, which mean so against this value we will get the forecasted value, and then we are going to calculate the error value. Against this we are going to get the error value, and then we are going to find out the different type of measures such as root mean square error, mean absolute scaled error, and so on. Okay, and then based on that we are going to select the best method. So this is called as out of sample forecast accuracy based to select the better model. Okay, now the third approach is the latest one, which is the better approach, which is called as time series cross validation, which is also known as the rolling horizon. Okay, rolling forecast origin approach. Okay, so in a rolling forecast origin is what we are doing is, let me show you in a detail because we can do
deal the time series cross validation in a number of ways. As you can see that over here, so basically if this is the entire data set we have, okay, so the blue dot is basically the training data, and then one step ahead we are using to predict it, and then based on this red we are going to calculate the error. Similarly over here, this is again a one step ahead forecasting. Now as you can see that the in sample data set we are start increasing. Now till over here we have an in sample, this is one step ahead out of sample data set, and based on this we are again calculating the error. So let me show you in a much detailed version. Let's say we have these 25 observation, these are the total 25 observation we have. Okay, what we have done is we consider out of these 25, 15 observations are the training data set or a in sample. Okay, like from here to here, these are the white colors, okay, boxes. And then because we are using the rolling origin approach, in a rolling origin I am saying that the first origin is going to be 15. So this is my origin, and my forecast horizon is 3 period ahead. Okay, so which means till 1 to 15 I am going to use in sample data set, and then from onward we are going to predict the values. Okay, that is the forecast horizon 3. So we are going to get the prediction value against these three numbers, and then we have the actual data set. Okay, so we are going to calculate the forecast error against this actual data set and the forecasted value, and we will get the errors. Okay, so these are the three error values, and then we can calculate different type of measure of accuracy against these errors, such as root mean square error, mean absolute percentage error, and so on. Okay, once we have calculated this one against the origin 15, then we are saying that now we want to roll the origin from 15 to 16. So which means now we have observation from 1 to 16. Okay, and again we are predicting the three forecast horizon. Okay, again for model fitting we are using this data set, and for testing the model we are using these three data set, and then we are saying roll the origin. Now we are using origin is 17th up till 17th, which means 1 to 17 is our data set, and these are the forecast horizon. So the advantage of this method is that is basically we are increasing the in sample size. Okay, so earlier we were using 15 data set to fit the model, then 60, then 17, then 18, and so on. Okay, so in this particular diagram we are basically using the rolling origin approach, where we have constant holdout sample size. Okay, so which means every time we are predicting future three forecast horizons, whereas the second approach which you can use to find out the rolling origin forecast error is using a non-constant holdout sample size. So as you can see that till over here we have we are using different in sample sizes of the data set, or you can say the training data set, whereas the forecast horizon was 3. Okay, whereas over here we have the forecast horizon 2, we have forecast horizon 1. So which means in order to generate the error we are using one step ahead forecast error, we are using two step ahead forecast error, we are using three step ahead forecast errors, and so on. Okay, whereas over here is 3. Now it's up to you, either you can adopt this approach or this approach. Whereas we can also adopt the third approach. Over here in that approach we are saying constant in sample. Constant in sample mean we are saying that every time we are going to use, let's say, 15 data set to train the data, and then the remaining data we are going to use the forecast horizon. So as you can see from this diagram, when the origin is 15, so which means from 1 to 15 I am using the data set to train the data set, train the model, and then these three values are going to use as to get the forecast error. Okay, then we are going to remove this first observation, and now I'm going to use this data set to train the model from 2 to 16 Again, we have the 15 number of observation in a sample, and then these three are going to be my forecast horizon. Okay, then when the region is 17, so the two first observations are going to be removed. So again, we have the 15 observations to train the model, and these three are the forecast horizon. So I hope you got the idea regarding the rolling regions. So we can apply these three approaches, but right now, when I am going to implement these methods in R, so I am going to apply this particular approach. Okay. So, in order to find out the forecast evaluation in sample and out of sample, we can use the function of accuracy from the forecast package for both in sample as well as the out of sample. Okay, as well as if you want to use the gray package, then the function is measures. Okay, so let me first calculate the in sample and out of sample forecast errors with respect to accuracy function as well as measures function, and we will see that these functions are going to report us different type of measures of accuracies, such as root mean square error, mean absolute percentage error, and so on. And then at the end, I'm going to calculate the rolling forecast origin forecast accuracy. But of course, before calculating the in sample forecast error and out of sample as well as rolling horizon, we need to fit the forecasting model. So for that, first of all, I am calling these two libraries, forecast and gray box. And of course, first of all, you have to install it so that you can do it in packages. You can go to install and write down the name of the package such as forecast. Okay, uh, forecast. And then once you have click over it, then install. So make sure your computer is connected with the internet so you can install. So once the package is installed, then call these two packages. Now, with the help of this command, what I am going to do is I am going to read the time series data. Okay, and this data set is available in the same folder where I have developed this particular project. Okay, that is basically TS2. Okay, that is this one. So I am saying that read this data file, okay, which means scan, that is the function which is going to read this ts2.txt file. Then I am saying this is basically the monthly data and the starting point is January 2011. So I am mentioning the start value is January 2011 and the frequency is 12 mean. We know that in a 1 year we have 12 months. So this is the monthly data, and then I am saying that convert into the TS, which means time series data. So after converting into the time series, we are going to store in a TS2 plot, TS2 variable. Okay, and these are the 60 observations. So let me plot this one. Okay, so this is the you can say time series plot. So as we can see that it look like a increasing trend. Okay, so if you want to see the observations, so you can write on TS2. So this is January 2011 to December 2015. Now I'm going to read out of sample data. Okay, so which I have already stored in a separate file, which is over here in a ts2. Okay, so and the starting point is January 2011, and again this is the monthly data set. This is ts2 dot test, that is basically the holdout sample, or you can say test data set. Okay, now I am storing ts2, which is basically the training data into a y variable and testing data into y dot test, and then I am basically setting the forecast horizon, which is basically the 12 month, that is equal to the length of the y dot test variable. Okay, in order to find out the forecast errors, what we need to do is first of all we need to apply the forecast method. So in from the forecast package, I'm using a function called ETS. Okay, and then I'm giving the name of the variable which it is going to be used to fit the model. Okay, the beauty of this ETS function is that is out of those 30 to 36 models, this ETS function is going to pick the best forecasting method for this particular data based on the kind information criteria, the chi-information criteria corrected, or the Bayesian information criteria. The model which is giving us the lesser values of the chi-information criteria or Bayesian information criteria, so this function is going to pick that particular model. So first of all, I am fitting that model, and then when I am calling this particular variable, because we have stored that fitted model in this variable, so it is showing us what kind of forecasting method it has applied, okay, and then giving us the values of the parameters alpha, beta, gamma, giving us the initial values as well as seasonal index. It is giving us the chi information criteria, chi information corrected, as well as Bayesian information criteria. Now, with the help of forecast function, I am for predicting the future values. So this is fit.ets, which mean I am saying that because in this variable we have this particular model. So using this model, predict the h is equal to h, which mean predict the future 12 values, because the value of h was 12. Okay, as you can see, this is the 12 value. So now I am forecasting with the help of ETS. Okay, so these are the future forecasted value. These are the prediction interval at 80% prediction interval. This is at 95%. Now I'm plotting this one. Now I'm using the line of the test data. So this is blue line is basically the predicted values. The gray is basically the prediction intervals, and red is the test data. Okay. So if you want to apply a particular model using the ETS, you can also mention like this way. If you want to apply a particular model, which I am not going to do that, you can do by yourself. Okay. So similarly, in the forecast package, we have also another function which is called as auto.rema. Like the ETS is going to pick among the different exponential smoothing method the best one based on the chi information criteria and the Bayesian information criteria. Similarly, auto.rema is going to pick from the REMA models, okay, as well as from the seasonal REMA models, that is autoregressive integrated moving average, the best one. So let me fit this model as well. Okay, so you can check from the this one that what kind of model they have applied on this data set. Okay, and these are the different elements, these are the forecasted values. But for over here, the important component is we are interested in, that is in sample forecast accuracy we want to find out. Okay, how we can do that? So I'm using the function called accuracy from the package of forecast. Okay, so I am saying accuracy and then the name of the variable in which we have the fitted model, which is f.ets, that is exponential smoothing model. Okay, so this variable has the prediction values. So with the help of this one, if I am run this one, okay, that is auto underscore ets. So let me uh, again run this one. So this is, as you can see, that it is showing us the training set forecast error. So training set mean in sample, which mean that is basically they have used the data set from 2011 to 2015, which was this one, not the test data set it has used. Okay, so as I mentioning over here, if you can go this one, it is going as only the in sample forecast accuracy. Okay, if you are going to use this particular component in the accuracy function, it is going as both in sample and out of sample. If I'm going to use this approach, then it is going as the out of sample. So let me run these command to show you, like if I'm running this one, so I'm calculating the accuracy with respect to REMA model. This is the training set, this is training and test, which means this is the in sample forecast accuracy, this is the out of sample forecast accuracy. This is mean error, this is root mean square error, this is mean absolute percentage error, this is mean percentage error, mean absolute percentage error, mean absolute scaled error, and so on. So these are the measures which the accuracy function provides us. Okay, now let me calculate only the in sample mean training set forecast accuracy with ETS model as well as ARIMA in order to check which method is better. Then with the help of this command, what I am going to do is I am going to combine the results of these two functions or variables in one variable, that is f dot all. Okay, and then over here I am saying that I want to see which are the ARIMA ETS models result, which are ARIMA. Okay, I'm giving the row names and then f dot all. As you can see that from the selected model of ETS, the mean absolute percentage error within a sample as well as the ARIMA model. Based on ME, we can see that ETS is performing better. Root mean square error, ETS is performing better. MAE based, ETS is performing better. Okay, so overall, ETS model is doing well on this particular data set if we are talking about in sample forecast accuracy. Let me calculate out of sample forecast accuracy using the accuracy function. So for that, we are saying accuracy, then f dot ets, that is the name of the variable in which we have the forecasted value using the exponential smoothing model, and then dollar sign mean. Dollar sign mean is taking the predicted value, okay, up to 12, okay, because the forecast horizon we were considering 12, and then y dot test, having the variable having the data set of out of sample data set. Now using these 12 values and these actual 12 data set, calculate the forecast accuracy of the exponential smoothing, calculate the RIMA model with the help of this function, and now I am calculating, reporting it. Okay, as you can see that if we are talking with respect to out of sample forecast error, ANIMA model is better one compared to ETS. So which mean in order to going to select with respect to out of sample, so ARIMA is doing good. So that's why this these approaches are very good. So it seems that ETS is overfit model for this particular data set, whereas ARIMA is doing good in a out of sample forecast accuracy. Okay, similarly, if you are interested to use the function Meyers, which is from the gray box package, okay, this package, okay, which are basically providing us more measures of accuracies. So how you can calculate the in sample as well as out of sample. So before using this particular function, I am running a command called options. Scipin is equal to triple line. Basically, the beauty of this function is if any particular function is returning the scientific notation answer, so it is going to force them that they should not provide us the answer in a scientific notation. Okay, now in order to calculate the measures of accuracy using the Meyers function in sample, we need to tell Meyers, okay, then y, that is the training data set, the variable in which we have the training data set, and then we are mentioning the in sample forecasted value or the fitted value. So I am saying f dot ets, that is the name of the variable in which we have the forecasted model, dollar fitted, that is the in sample predicted values, okay, and then comma, we are mentioning again the actual variable which is y. So if I'm going to run it, okay, and then you can see that this is basically the in sample forecast accuracy errors. Okay, so as you can see that using the Meyer function, it is giving us the more measures of accuracies: ME, MAE, MSE, MPE, MAPE, okay, SCE, scaled mean absolute percentage error, scaled mean square error, mean absolute scaled error, root mean absolute error, and so on. Okay, so similarly, if you are interested in out, instead of using fitted, you have to use the mean. Now it is going as the out of sample forecast error. Now you can see based on out of sample, it seems that RIMA models are doing good compared to the exponential smoothing models, okay, for this particular data set. Now, the most important component which we are going to use is the rolling horizon forecast accuracy, and I am adopting this particular first approach. Okay, that is this one. So, what is how we can do that? How we can calculate the rolling horizon forecast horizon? First of all, I am combining the in sample and hold out, or you can say the test data set. So, how can I do that? I am saying that C y comma y dot test. So which mean y having the training data set, y dot test having the testing data set. And then I am saying that because the starting point of the actual data is January 2011, because it's a monthly data, and then I'm converting into the time series, so storing into the data variable. So this is January 2011 to December 2016. And then I am mentioning that the total observation, so these are the total number of values. So because we have the 6 years, 12 months, so 12 into 6, 72. So total observations are 72. So I'm mentioning in a variable 72 in a variable. So we are going to use further this particular variable. And then I want to find out the measures of accuracy of the future 3 step ahead. Okay, so if you want to find out the forecast accuracy 1 step ahead, write down over here 1. Okay, 2, so write down 2. If you are want to find out the forecast accuracy 4, write down 4. So I am setting the forecast horizon 3. And then origins means the number of origins. Okay, so these origin, like over here I was mentioning origin is equal to 15. So from 16 to onward it is giving us the 3 forecast error. When I'm saying origin 16, so it is giving us the 3 4 future forecast error. So how many number of origins we have selected? We selected 8, but over here I am setting the origins 9, because the actual data set we have, that is over here, this was the training data set. So what I am going to use is I am using from January 2011 to January 2016 was a training data set, and then testing is going to be start from here. Okay, so these 9 observations over the region I am going to use. Like, so first of all, once I've set this one, now I need to differentiate the actual data set, or you can say training data set, then holdout sample, which is a test data set, okay, and then the predicted values. So how we can do that? I am mentioning that set name, that means giving the name to the 3 vectors. Okay, so which mean I am saying that create 3 vectors, okay, which are the type of list. Okay, and then give the name to those vectors. One vector is called as actuals, then holdout, and then name. If I'm running this one, okay, and then I am calling this particular variable, which is data values, as you can see that they have created the 3 vectors. Right now these vectors are having no values, so these are only the names which we have given them. Okay, then I am saying that in this actual vector or a list, store the value data. Okay, so that is basically the entire data set we are storing in this particular variable. Okay, so now we can see that in this particular values we have this particular data set, right? Now as you can see that in actuals we have those data set. Now I am mentioning in a holdout, what you are going to do is calculate the mean, okay, and holdout values and in a mean. Okay, so I am saying creating a matrix and not giving any data values, and the matrix number of rows are equal to h. How many h? There's a 3 rows. Regions are is equal to 9, so 9 columns. And then the dimension names, okay, that is basically I'm saying create the list, okay, and paste it h1 to h, which mean the number of rows. So it is giving us the name of the row h1, h2, h3, because we have the maximum h is 3. Similarly, the we are giving the name of columns, okay, from 1 to regions, that is up to 9 columns. So with the help of this one we are creating the rows and columns. Now using, once we have created this one, now I am going to create the model fit in sample and out of sample. So I am saying that developing a loop for I in 1 to regions, which mean 1 to 9. Okay, so the loop is going to run 1 to 9. So first of all, I'm fitting the model. Okay, so I am saying ETS, that is select the best exponential smoothing model based on this function. I'm saying data, that is the variable in which we have entire data set, that is this one. And then I'm saying one column OBS. OBS is the name of variable in which we have the total number of observation, which is 72 plus I. Okay, when the loop start, the first value of the I is going to be 1, which means 72 plus 1 minus origin minus h. So what is the origin? That is 9 minus 12. So which means when the value of I is equal to 1, okay, this is going to be 1 to 1 loop, which means because this is 72 plus 1, 73. So 73 minus origin 9 minus 3. Okay, so 73 minus 12. So that means it is going to fit the model from 1 to 73, which means only one step ahead. Okay, so similarly, when I is equal to 2, when I is equal to 3, and so on. Okay, so basically it is going to give us nine different based on nine different regions, like as we seeing over here. Okay, so this is the model fitting, and after the fitting the model, we are storing in a variable called test model. And then with the help of this particular command, what I am going to do is I am basically eliminating the in sample observation, which means I am dropping those observation and only extracting the um, predicted values. Okay, so how we can do that? I am storing those values in a holdout variable. Okay, and this is basically how we are storing it, because I am saying bracket comma I, which means the second column, which means that's the observation against the year. Head is equal to data, so head means the first edge observation I want to see. Okay, so data minus C, minus means so those observations should be eliminated before this one, from 1 to this one. Okay, so that means if when the I is equal to 1, the first 72 observations are going to be eliminated. Okay, so only showing us the H number of or you can say the values which are basically the forecasted values. So if I, with the help of this one, we are basically dropping out the in sample values. Okay, now we are basically predicting the future values. Okay, so that is basically forecast, and then based on this variable in which we have the model fit, that is the test model. H is equal to H dollar sign mean, because basically we are taking only the predicted values, not the holdout sample. Okay, now if I run this particular loop, okay, so the loop is successfully completed. Now I am basically accessing these numbers, the holdout sample. Okay, as you can see, so because the H was 3, we have set these are the 3, so that means the 3 forecast horizon when the origin was this one. So let me write down the data. Okay, so when the origin was this one, because we have set the origin 9, so that means till ninth observation. Okay, so number of regions were 9 and the forecast horizon was 3, so that's where it is starting from over here. So this is the origin, this one, and then for the second time, that is this one, the third time, that is this one. Okay, so these are the three forecast value or regions, as well as the forecast horizon it is going to be used. So in a first time, when the I is equal to 1, it is going to use January 2011 to January 2016 to train the model, and it is going to produce against these values the predicted values. So these are the actual values which I have highlighted. Against these, it is going to predict the future values. When the origin was this one, when again in this particular loop I is equal to 2, so that the actual values are going to be this, and then it is going to calculate the predicted values with the help of this loop. Okay, now we have get the actual data set. Okay, now I want to get calculate the forecasted value. So how can I do that? So I can use the command data values dollar mean. Okay, so with the help of this command, I can get the predicted value because we have already calculated the forecasted value with the help of this one, with the function forecast dot this one. Okay, now, in order to calculate the measures of accuracy, I am calculating the errors. So how we can do that? Data value dot holdout. That is the variable in which we have the holdout data set. Okay, that is with the help of this one, minus data values dollar mean, the variable in which we have the predicted values. So that means the holdout value minus the predicted value. Okay, so if I run this command, I can get the error value against every forecast horizon. So let me show you the actual holdout data set. This is a holdout data set. This is the mean value, which means this 3500 minus this one, we will get the first error. This one minus this one, we will get the forecast error. This one minus this one, we will get the forecast error. Similarly, this one minus this one, we will get the forecast error, and so on. Okay, so once we have calculated those errors, now the one way is to report it. We can use the visualization box plot. So against different 9 regions, we can see the median error of the forecast. We can see the dispersions. Okay. Similarly, we can calculate by applying the formulas of mean error. So how we can do that? We are saying apply on the error variable, that is this one entire variable. Okay, up to 2 decimals, that is the mean. Okay, basically the second column of this error, that is mean values. Okay, so if I am going to run this one, and then with the help of this one, basically I am calculating the root mean square error. Okay, taking the square root of this one. So after taking the square of this errors, and then taking the absolute, I am calculating the mean absolute percentage error. Now I am saying that give the name of each row me root mean square error and mean absolute error, and then I am printing the results. So these are basically against the exponential smoothing models, rolling horizon based forecast errors. So this one is when the origin is 1, a root mean square, mean absolute percentage error, similarly against origin 2, okay, and so on, right? So I hope you got the idea. Like if we have, you want to find out how you want to find out in sample forecast error, how you can find out the out of sample forecast error, as well as how you can find out the rolling horizon based forecast horizon. So among these three, either you can report the out of sample forecast error or a rolling horizon are the better approaches to report the forecast horizon. Thank you so much. See you in the next video.